Hi, Stu Schwartz from MasterMathMentor.com. This is video BC22. The topic is the ratio and root tests, and it covers the BC manuals page 110 and 111. So far, there has been no one convergence test that always works for any series. But we now introduced a test that, interestingly enough, is effective on some of the most complicated series, yet is pretty much worthless on simple series. But for those, we have other easy-to-use tests, and we can rely on the ratio test, for the difficult cases. A case in point is to find whether summation n equals 1 to infinity of 1 over n factorial converges or diverges. This series passes the nth term test, but is neither geometric or a p-series, certainly cannot be integrated, and the limit comparison to either 1 over n or 1 over n squares get a limit of 0, which tells us nothing. We might think about a direct comparison test, but we need to have some sense whether the series is convergent or divergent to do so. So we will introduce the ratio test, which compares the general nth term to the general n plus first term. The ratio test looks at the series summation of a sub n, and lets L be the limit as n approaches infinity of a sub n plus 1 over a sub n, and looks at the absolute value of that. It is basically taking a comparison of the nth plus first term over the nth term. If L is less than 1, our series is convergent. If L is greater than 1, our series is divergent, and if L is equal to exactly 1, then the test is inconclusive. So let's try the ratio test with our series summation n equals 1 to infinity of 1 over n factorial. We start by setting up L, which is the limit as n approaches infinity of 1 over n plus 1 factorial over 1 over n factorial, and it's the absolute value of that expression. The ratio test usually takes up a lot of room, so be prepared for that. We can now flip the denominator and write this as the limit as n approaches infinity of the absolute value of n factorial over n plus 1 factorial. Students may not be familiar with working with factorials. This turns out to be the limit as n approaches infinity of the absolute value of. The numerator is n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1, while the denominator is n plus 1 times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. Everything cancels except the n plus 1 in the denominator. So this is the limit as n approaches infinity of the absolute value of 1 over n plus 1, which is equal to 0. And since L is less than 1, our series converges. It is important to include the absolute value sign unless you're absolutely sure that the terms will always be positive. Once we get to power series, you can't drop the absolute value sign as it is critical to the result. Secondly, realize that if you get infinity for the limit, this will indicate divergence, as nothing is stated about L being finite. And finally, realize that unlike the direct comparison test, the ratio test requires that the n plus first term be in the numerator and the nth term be in the denominator. In problems 2, 3, and 4, we are to expand the series and then use the ratio test to determine the convergence or divergence of the series. In number 2, we are given summation n equals 0 to infinity of 4 to the n over n factorial. Our first term is 1 because 4 to the 0 is 1 and 0 factorial is defined as 1. And then our subsequent terms are 4, 16 over 2, 256 over 24, 1024 over 120, plus dot, dot, dot. It might appear that this series is failing the nth term test, as the numerator appears to be getting bigger much faster than the denominator. But that is an illusion. For instance, when n is 10, we will have 4 to the 10th over 10 factorial. The numerator is 10 fours, while the denominator is 10 times 9 times 8, etc. And eventually, as n gets large, the denominator will be much, much greater than the numerator. The neat thing about the ratio test, though, is that if the nth term test is not obvious, you don't have to apply it. Just use the ratio test. So we look at the limit as n approaches infinity of 4 to the n plus 1 over n plus 1 factorial divided by 4 to the n over n factorial. On this and all other problems, we will save some time and space by immediately flipping the denominator. So we look at limit as n approaches infinity of 4 to the n plus 1 over n plus 1 factorial times n factorial over 4 to the n. 4 to the n plus 1 over 4 to the n is simply 4. And n factorial over n plus 1 factorial gives an n plus 1 in the denominator, as we saw on the previous problem. The limit as n approaches infinity of the absolute value of 4 over n plus 1 is equal to 0, so this is a convergent series. Number 3 reads summation n equals 1 to infinity of 4 to the n over n times 3 to the n. When we expand, we get 4 thirds plus 16 over 18 plus 64 over 81 plus 256 over 324, etc. It appears that this is passing the nth term test, but it is not necessarily obvious. But again, we can bypass that by simply using the ratio test and look at the limit as n approaches infinity of 4 to the n plus 1 over n plus 1 times 3 to the n plus 1 times n 3 to the n over 4 to the n. We will deal with several things here. First of all, we will look at 4 to the n plus 1 over 4, and that is a 4 upstairs. We will look at 3 to the n over 3 to the n plus 1, and that is a 3 downstairs. And finally, we have an n over n plus 1, and the limit as n approaches infinity of that is simply 1. So this is the limit as n approaches infinity of 4 thirds, which is 4 thirds. Since this number is greater than 1, this series is divergent. 4 reads summation n equals 0 to infinity of n times 4/5 to the n. We know that 4/5 to the n is a convergent geometric series, but when we multiply that by n, that might change things. We write out the terms and we get 0 plus 4/5 plus 32 over 25 plus 192 over 125 plus 1024 over 625. And it appears that the numerator is getting bigger than the denominator. However, that is not proof, and we'd need to look at more terms to determine whether this passes the nth term test. It really is easier just to apply the ratio test. So we look at limit as n approaches infinity of the absolute value of n plus 1 times 4 to the n plus 1 over 5 to the n plus 1 times n 5 to the n over n 4 to the n. We will deal with three things here, the 4, the 5, and the n's. For the 4, we have 4 to the n plus 1 over 4 to the n, and that's a 4 upstairs. For the 5s, we have a 5 to the n and a 5 to the n plus 1, and that's a 5 downstairs. And like the problem before, n plus 1 over n, limit as n approaches infinity, is simply 1. So this is the limit as n approaches infinity of 4/5, which is 4/5. So this is a convergent series. In numbers 5 through 7, we are again asked to expand the series and then use the ratio test to determine whether the series is convergent or divergent. In number 5, we have summation n equals 0 to infinity of n squared 2 to the n plus 1 over 3 to the n. We generate our term 0 plus 4/3 plus 32 over 9 plus 144 over 127 plus 512 over 81 plus ... It appears that this will fail the nth term test. After all, there is a higher power of 2 than 3, and there's also an n squared upstairs. So it appears that the numerator will get bigger much faster than the denominator. But let's check that out with the ratio test. We look at limit as n approaches infinity of the absolute value of n plus 1 quantity squared times 2 to the n plus 2 over 3 to the n plus 1 times 3 to the n over n squared times 2 to the n plus 1. We have to worry about the 2's, the 3's, and the n's. For the 2's, we have a 2 upstairs. For the 3's, we have a 3 downstairs. And the n plus 1 quantity squared over n squared as n approaches infinity is equal to 1. So this is the limit as n approaches infinity of 2/3, which is 2/3. So believe it or not, this is a convergent series. Number 6 is the series summation n equals 1 to infinity of 3 to the n over negative 2 raised to the n plus 1 times n. This is a reverse of number 5. Now it appears that most of the big terms are in the denominator. Also, this is an alternating series, which seems to indicate that it would be convergent. But again, let's check it out. Our terms are 3/4 minus 9/16 plus 27 over 48 minus 81 over 128 plus 243 over 320 plus ... We look at limit as n approaches infinity of the absolute value of 3 to the n plus 1 over negative 2 to the n plus 2 times n plus 1 times negative 2 raised to the n plus 1 times n over 3 to the n. There are three things to worry about here, the 2's, the 3's, and the n's. Now we have a negative 2 downstairs, we have a 3 upstairs, and again the n's cancel. So this is the limit as n approaches infinity of the absolute value of 3 over negative 2. And this is where the absolute value comes in. This is equal to 3/2. Since this number is greater than 1, this is a divergent series. Number 7 is definitely a cut above in terms of difficulty. Summation n equals 1 to infinity of n plus 1 factorial over n to the n. We write our terms out. 2 plus 6 over 4 plus 24 over 27 plus 120 over 256 plus 720 over 3,125. It appears that the denominator is getting bigger at a much faster rate than the numerator is, but of course that all tells you that this could converge, not that it does converge. So we will now apply the ratio test, and we look at the limit as n approaches infinity of the absolute value of n plus 2 factorial over n plus 1 raised to the n plus 1 times n to the nth over n plus 1 factorial. How do we simplify this expression? First of all, we have an n plus 2 factorial over an n plus 1 factorial, and that just gives us an n plus 2 upstairs. For n to the n over n plus 1 raised to the n plus 1, we can get a little bit clever and write this as n over n plus 1 to the n, multiplied by n plus 1 on the bottom. That would give us an n to the n upstairs, and an n plus 1 to the n plus another n plus 1 on the bottom, giving us our n plus 1 to the n plus 1. And now the limit as n approaches infinity of n plus 2 over n plus 1 is simply 1. So we have the limit as n approaches infinity of n over n plus 1 raised to the n, which you should recognize as 1 over e, making this convergent. If you don't recognize the limit as n approaches infinity of n over n plus 1 to the n as 1 over e, let's show that result by logarithmic differentiation. We've let x equal the limit as n approaches infinity of n over n plus 1 raised to the n. And we now take the natural log of both sides. And we get the natural log of x is equal to the limit as n approaches infinity of n times the natural log of n over n plus 1. We can do several things with this expression. We can divide n plus 1 into n and get 1 minus 1 over n. And we can write n as 1 over 1 over n. So natural log of x is equal to the limit as n approaches infinity of numerator, natural log of 1 minus 1 over n, over denominator 1 over n. And now we apply L'Hopital's rule. We get the limit as n approaches infinity of numerator 1 over 1 minus 1 over n times 1 over n squared over denominator negative 1 over n squared. The 1 over n squares cancel, and when we apply the limit, we get the natural log of x is simply equal to negative 1. Therefore, x is equal to e raised to the negative 1, or 1 over e. Note that the ratio test is inconclusive with summation n equals 1 to infinity of n plus 3 over 2n minus 1. Because if we apply it, we will get the limit as n approaches infinity of n plus 4 over 2n plus 1 times 2n minus 1 over n plus 3. And when we take the limit as n approaches infinity of that, the absolute value of that expression, we get 1. This will always occur with rational expressions involving only polynomials or polynomials under radicals. But luckily, we have other tests on which to fall back on. Obviously, in this example, the series is divergent as it fails the nth term test. The final convergence test is a test that is no longer a part of the BC curriculum. However, we will present it here because it's easy to use and sometimes helpful to students. It is called the root test. Given the series summation a sub n, we let L be the limit as n approaches infinity of the nth root of the absolute value of a sub n, which could also be written as the limit as n approaches infinity of the absolute value of a sub n raised to the 1 over n power. Like the ratio test, if L is less than 1, our series is absolutely convergent. If L is greater than 1, our series is divergent. And if L is equal to 1, our test is inconclusive. The root test works well when either the numerator or the denominator, or both, are raised to the nth power. That is true on problems 8 through 10. Number 8 reads summation equals 1 to infinity of 2 raised to the 2n power over n to the n. We write out our terms. 4 plus 16 over 4 plus 64 over 27 plus 256 over 256 plus 1024 over 3125 plus dot dot dot. We look at the limit as n approaches infinity of the absolute value of 2 to the 2n over n to the n, and that is all raised to the 1 over n. Remember that powers to powers simply multiply the powers, and therefore we have the limit as n approaches infinity of 2 squared, which is 4, over n to the first. And that is equal to 0, meaning that we are looking at a convergent series. 9 is summation n equals 0 to infinity of the quantity 4n minus 3n cubed over 5n cubed plus 1 raised to the n power. Writing the terms out, we get 0 plus 1/6 plus negative 16 over 41 squared plus negative 69 over 136 cubed plus negative 176 over 321 raised to the 4th power plus dot dot dot. Note that this has some negative terms to it. Whenever you see an expression raised to the n power, the root test is perfect. So we look at the limit as n approaches infinity of the absolute value of quantity 4n minus 3n cubed over 5n cubed plus 1, quantity raised to the n, and then raised to the 1 over n power. And n raised to the 1 over n power, multiply the powers, and the n's cancel, so we're simply left with the limit as n approaches infinity of 4n to the minus 3n to the third over 5n cubed plus 1. We could use L'Hopital's rule here, but we simply look at the highest power terms. We get negative 3/5, and the absolute value of that is 3/5, which is less than 1. Again, we're looking at a convergent series. 10 reads summation n equals 1 to infinity of negative 2 raised to the n power over n to the 4th. When we write out the terms, we get negative 1 plus 2 over 16 minus 4 over 81 plus 8 over 256 minus 16 over 625 plus dot dot dot. And this is an alternating series. This is an example of a problem that has just the numerator raised to the n power. We still use the root test. We look at the limit as n approaches infinity of the absolute value of negative 2 raised to the n over n to the 4th, the whole thing raised to the 1 over n power. The numerator is simply the limit as n approaches infinity of 2 when we eliminate the absolute value sign. The denominator is n raised to the 4 over n power. The limit as n approaches infinity of n to the 4 over n power is an example of infinity to the 0. And this particular one is equal to 1. Therefore, 2 over 1 is 2, and our answer is divergent. If it is not clear that the limit as n approaches infinity of n to the 4 over n is equal to 1, we show a small proof of that. We let x equal to the limit as n approaches infinity of n to the 4 over n and take the natural log of both sides, getting the natural log of x is equal to the limit as n approaches infinity of the absolute value of n raised to the 4 over n, which is 4 over n times the natural log of n. We now apply L'Hopital's rule to that, and we get natural log of x is equal to the limit as n approaches infinity of 4 over n, and that is equal to 0. And since natural log of x is equal to 0, x is equal to 1. Some of the more complex expressions we have seen use different types of expressions in the numerator and denominator. We will express them in terms of power. The most powerful one is at the top of the pyramid, n to the nth. The next most powerful is n factorial, followed by any constant. I will use 5 to the n, and the least powerful is n to the 5th. In general, the summation of an expression which is less powerful on top and more powerful on the bottom is convergent, while an expression which is more powerful on top and less powerful on the bottom is divergent. This is a good rule of thumb. It's not a proof, and you cannot utilize it in the AP exam. You will have to show your tests, but you will know whether your answer is right by following this rule. Let's see these with 4 problems. We see 4 expressions, and we'd like to determine whether they are convergent or divergent, and no work is required. Let us show that we can determine this very, very quickly. 11 reads summation n equals 1 to infinity of n to the 5th over n factorial. N factorial is the most powerful, n to the 5th is not. So this is a less powerful over a more powerful expression, and therefore it is convergent. Number 12, summation n equals 1 to infinity of n to the n over 20 to the n. N to the n is the most powerful. 20 to the n is less powerful than that. So therefore this is divergent. Summation n equals 1 to infinity of n factorial over n to the n. Again, n to the n is the most powerful, and n factorial is slightly less powerful. Therefore, this is convergent. Finally, 14, summation n equals 1 to infinity of 30 to the n over n to the 60th power. Note that the relative sizes of the constants makes no difference, that 30 to the n is more powerful than n to the 60th. This is divergent. All the convergence tests have now been taught. The next video will review them all and give you a sense of which tests to try first and which are likely to quickly and painlessly give you a decision as to convergence or divergence of the series.